We're told the vast population grows according to a logistic growth model. So there's two things that come from our textbook. There's the differential equation that represents a logistic growth model, and then there's the solution. The textbook derives the solution to that equation, okay, depending on the initial population. K, now one point of confusion here with WebAssign and with our textbook is that our textbook uses capital K to be the carrying capacity. It's just this right here, okay. Capital K is the carrying capacity. So that can be confusing because they're talking about a growth constant K. The growth constant is R in the textbook. So the letters K and the letter R, they're kind of switched up there. So if you wanted to rewrite the textbook's formula into WebAssign's notation, you can still use P sub 0. Let's use C for the carrying capacity. I'm not sure why they didn't do that in the first place. Times E to the K times T, where K is the growth constant. And then everything else can go in that formula there. But just remember, when you see R in your textbook's formula, that's K for this WebAssign problem, because that's the growth constant. So to figure out what K is, we should plug in the information we're given. Let's see. The lake has 2,000 bass. That was like the initial population, it seems. So I'm going to put that as P sub 0. That was a year ago. We've got that P sub 0. So 1 year ago was 2,000. So maybe this is P of 1. After 1 year, we have 2,500. Let me see. Yeah, I think that's what we got to do. So what they've said is after 1 year, assuming T is in terms of years with their logistic growth model, then we have 2,500 for a population. So I plug that in here. And then we have P sub 0. The initial population was 2,000 before that change. The carrying capacity is 20,000, because capital K in our book's formula is the carrying capacity, times E to the R, which we don't know, times T, which is 1 in our problem, all over our carrying capacity, 20,000, minus the initial population, plus the initial population, times E, again to the R, times T power, and T is 1 in this case. So this is the equation we have to solve. If we solve for R, that's like solving for their lowercase k. So it's just kind of a messy algebra thing to unravel here. We can do some simplifying too before we go too far. Here's the left side. Got 2,000 times 20,000. So we got 40 million. I have to write with this mouse. I used to have a pad, but they kept breaking. The mouse works. It hurts the fingers after a while. Okay, so 20,000 minus 2,000 makes 18,000. And then we got 2,000 e to the r. So what you want to do with these types of problems, when you're trying to solve for a variable and it's a numerator and the denominator, your goal should be to first get it out of the denominator, get it out of the bottom of the fraction. So I'm going to multiply both sides by 18,000 plus 2,000 e to the r. Okay, because that will make this cancel out in the denominator. So when we do that, we're going to have 2,500 and then a parentheses 18,000 plus 2,000 e to the r. And now the denominator's gone over here, so we just have 40 million e to the r. And now that you've got the variable out of the denominator, now your goal should be to collect only variable terms on one side of the equation. So this is a variable term, this is a variable term, but in order to get it collected, I have to first distribute. Oh boy, the numbers are going to get bigger. 2,500 times 18,000, 45 million. There we go. And then 2,500 times 2,000. Didn't we already No, we didn't do this. 5 million times e to the r. Okay, and like we said, we want to collect all the variable terms in one side. Actually, they can combine like terms because this and this are the same. So we can just subtract. This won't be as hard as I thought. 5 million e to the r. Subtract that from both sides. So we're left with, on the left side, 45 million. And on the right side, we've got 35 million e to the r. So if you're trying to get e to the r by itself, you just want to divide 35 million from both sides, right? So if we do that, we got 45 million divided by 35 million. Oh, I think again it's 1.28, right? 45 divided by 35 gives us 1.2857. Let's just carry out some decimals to make WebAssign happy. 1.2857114 equals e to the r. So the last step is to take a natural log of both sides. And that gets you r. I think I actually remember WebAssign keeping it as a fraction too. So let me just do this without turning that into a decimal too. Because here, back here, before we did this 1.2854, that was 45 million over 35. That equals e to the r, right? Or you can simplify this fraction. Let's see, that's 9 over 7, which equals e to the r. And then if you take a natural log of both sides, WebAssign might prefer this. Same thing, right? I just didn't turn this into a decimal. 9 divided by 7, yeah. So if you keep it as a fraction, this would be your answer. If WebAssign's okay with decimal equivalents, that would be your answer. But it doesn't say. So I think you should, to be safe, you should go with the non-decimal answer. So here, when you divide 45 million by 35 million, simplify that fraction. That's 9/7 for my problem. Okay, so K, I'm going to answer is natural log 9/7. Okay, that's the first part of the problem. The second part says, what are the units of K? And so this probably is confusing to a lot of students, like on how to even start this, because it doesn't really come up so much in our text. But what you could do is what you might have done in a chemistry class before. Think about how units need to cross cancel in order to get like the final units you want. In this equation here, we need units in terms of population. Right? Those are our units. That's a certain number of people. So in order to make that happen, we need to make sure that we don't have any units involving time, any units involving any other measurement that are in our final answer. And so when we're talking about K, which is R in our textbook's notation, the units need to be such that time is canceled out, right? The final answer is supposed to be in units of population. You can't have time in there at all. So R times T, we need to make sure that R is 1 over whatever time units we have, 1 over years. That way, when you multiply something that's in units of 1 over years times years, which is what our T variable is in, they cross cancel. And now we don't have a unit that's in terms of, we don't have years in our final answer. So the final answer here for K is 1 over years, or they might say years to the negative first power. Okay. There's no other place with it. Same thing in the denominator. If this is like T squared for some reason, let's see. Yeah, that'd have to be years to the negative second, right? So that years squared times years, 1 over years squared times years squared would cancel out to get rid of your years unit. Last question, how long will it take for the population to grow from 2,000 to 10,000? Now that we know R, this is really just a matter of plugging in. Let's see, oh no, we're going to be solving for T. Let me clear the board here. Let's plug in what we know. The population starts at 2,000, and we want it to end up with 10,000. So we want 10,000 for our final population. 2,000 is our starting population. The carrying capacity, we're assuming, hasn't changed, so 20,000. We have E. Now we found out K, or in this case R for our textbook's notation, that confusing stuff. Oh, actually I forgot, was it 9/7? I think it was 9, let me check. 9. Yeah. Natural log 9/7 was the growth constant. T is the variable. So it's just kind of a longer plug and chug problem. We got 20,000 for our carrying capacity, 2,000 for the P sub 0 population. We got 2,000 times E to the natural log 9/7 times T. I think, yeah, the algebra is going to be the same. So I'm going to pause here and let students finish this in case they have the same randomization. But it's the same thing as what we just did with the first problem when solving for K. Right? You got to simplify this, and then in order to get your variable t by itself, you need to get it out of the denominator. So you're going to have to multiply by this denominator here to both sides, just like we did in the first problem. Okay, multiply to both sides, use the distributive property, make that 10,000 multiply to everything inside, and then combine like terms on the right side of the equation.